Welcome to Target IAS. I am Prakash Rajput. In the previous video, we have learned some applications of Gauss law and we have learned the use of Gauss law, how to use this. So now here is one problem where we want to find E and D, that is electric field intensity and electric flux density due to coaxial cable. So here is my coaxial cable which is having one inner conductor and one outer conductor, and charge is present over their surfaces. So here is on this inner conductor of radius A have charge present over its surface, it's positive, and for the outer conductor have charge on its surface as negative. So here the surface charge density for inner conductor, wait, here the surface charge density for inner conductor is rho s I, and for outer conductor suppose it's rho s naught. Now since the all the flux lines of this inner conductor will cross this outer conductor, this means that the charge on both these will be equal because same flux will cross, and as this is same flux is crossing, so the charge magnitude will be same. So we can say that the charge q inner magnitude will be q outer, just the minus sign will be there. So if I take inner charge as q and outer charge as minus q, so in terms of their surface charge density also I can write, if this is a surface charge density, so I can multiply the inner surface charge density into the surface area of the inner charge, that will be 2 pi radius, that is a, and into height of the this line charge, and for minus q also it will be minus rho s naught into, as the cylinder has a radius of b, so it will be here 2 pi b, and the height will be same, so 2 pi bh. So you can see the relation of the outer surface charge density with inner surface charge density as rho si into this will be a by b. So this is the relation between the surface charge density of both the surfaces. So we can write electric field intensity and displacement flux density in terms of any of the surface charge density, and then we can relate with both of them. So now we will apply Gauss law on this surface. So let us suppose the surface, if I take a Gaussian surface inside this cylinder, so I what the Gaussian surface will be, it will be also a cylinder of some radius. Suppose I'm taking in cylindrical coordinate system because I'm taking cylinder. So suppose let's just say for case 1, suppose let us say the Gaussian surface has a radius rho, which is lesser than the inner conductor radius for case 1. So the value of the rho will varying from 0 to a, 0 to a. So what it will be? Now we will apply Gauss law. So what the Gauss law says is that d dot ds will be equal to the charge enclosed. Now see, these are conducting surfaces. So all the charge which is present for this conducting surface will be present on the surface, as I have told earlier. Will be present on the surface. It will get distributed uniformly over the surface for conducting surfaces. So there will be no charge inside the this cylinder. There will be no charge inside this cylinder. So for a cylinder of radius 0 to less than a, there will be no charge enclosed. So you can say that for this range, q enclosed will be what? 0. So this means that electric field intensity in this region or displacement flux density will be also 0. So this will be 0. This means that d is equal to 0, and this means that epsilon naught E is also 0, which means that electric field intensity is 0. So for inside the coaxial cable, I mean for the surface 0 to A of 0 to A, the displacement flux density and the electric field intensity both are 0. So now we will take case 2. So we will take a Gaussian surface such that its radius lies between A and B. Its radius lies between A and B. So what happen is, now its radius is lying between A and B. So what will be the Gaussian surface? It will be somewhat in between, having radius rho. You can imagine it. So it will be something like this. If I complete this, and this is having radius rho. So now we will apply Gauss law in it. Now we will apply Gauss law in. So what the Gauss law says, it's d dot ds equals to the charge enclosed in it. Now see that the whole inner conductor is enclosed by the this Gaussian surface, which is shown here in green. So this whole inner conductor is enclosed, which means that the charge on the inner conductor, that is Q, is being enclosed. So we can write this enclosed charge as the charge of the inner conductor, which is nothing but Q, and we can also write this in terms of the surface charge density, which is rho si into 2 pi a h. 2 pi a h. Now what it will be, as the ds vector. Now as I've told earlier, for line charge, here for this top surface and bottom surface, the d dot ds will be 0, because for the top surface the displacement flux density, I mean the surface differential surface vector will be in the upper direction, and for the bottom surface it will be in the downward direction. So if you consider the rho phi z axis, so it will be on the z direction, and the displacement flux density will be in the rho direction, will be here somewhat. This will be d, and this will be the ds vector. So both are perpendicular. So for the top and bottom surface, the d dot ds becomes 0, only the radial component remains, and for that the theta is 0, which means that d dot ds becomes d integral ds and differential surface of the curved surface of the cylinder. So that will be 2 pi rho h, because I am taking radius rho for the Gaussian surface. So here it will be rho si into 2 pi a h. So what are the things that are cancelling? Here 2 pi and h gets cancelled. So what is remaining? That d is rho si divided by this can be written as a by rho. So if I write in vector form, this will be in the direction of aero cap, right? So this will be the value for displacement flux density. And if I write, so now if I want to write for the value of E, what it will be, I can simply divide this value by epsilon naught if I am considering free space, or by epsilon if there is some dielectric or some other material than the free space. So rho si a by epsilon naught rho, this will be the value of electric field aero in the aero cap direction only, because D and E are both in same direction. Now this result can be think of in another way also. If I, what is here the rho si, if I write this d vector, no, not d vector, suppose I want, because E relation are more familiar, I guess you are more familiar with. So rho si I can write as q by 2 pi a h, right? q by 2 pi ah, and the other things are a by epsilon naught rho aero cap. So here this a and a will get cancelled. What is this q by h? If you consider this conductor as a line charge, if you consider this conductor as a line charge, because there is no charge inside this surface, I can consider this uh, conductor as a line charge having line charge density of, what is the value of rho q here, if you see. So I can consider, if I write q by h, if I write q by h, this means the line charge density q by h, charge upon my length, it will be rho si into 2 pi a, right? So for this, if I replace this q by h by some line charge density rho l, where rho l is nothing but q by h, charge per unit length basically. So you can now write this as 2 pi epsilon naught rho aero cap. So if you remember this relation is, what is this relation? This relation is for the electric field due to an infinite line charge. So you can also relate this coaxial cable with that, if you are considering the Gaussian surface in between the conductors, right? So this is for that. Now we will consider a Gaussian surface outside this, outside both these conductor, because I have considered for A to B. Now I will consider the radius for case 3. I will consider the radius of the Gaussian surface. It will be greater than B. It will be greater than B, or I can say that rho will be greater than B, less than infinity for a range value. So I will apply Gauss law again. So d dot ds equals to, now what happened is, for a Gaussian surface which is present outside this uh, both these conductors, what happened is, charge q because of this and charge of minus q because of the outer conductor both are enclosed. So total charge becomes q plus q of minus q, which makes it 0. So this means that d dot ds 0. This means that d is 0, which means that E is equal to 0. E is equal to 0. So you can see that the electric field intensity or the displacement flux density for an coaxial cable is just present inside this region, which is in between both these conductors, which is in between both these conductor. You can also imagine that, because this is why this is happening, because all the flux line which are uh, emerging from the positive conductor, which is inner conductor, will get converge in the negative conductor, and there will not be any flux lines going outwards from here, right? So that's why the electric field intensity and d both lie in this space only. Inside this and outside this both are 0. And we can plot this variation also, variation of E with radius of the Gaussian surface rho. So if I write the E value for all the ranges that are from 0 से लेकर के A and A से लेकर के B and B से लेकर के up to infinity. So for the upper part, for the 0 to A range it is 0, and for the this range B to infinite it is 0, and what is for this range, it is rho si into A by epsilon naught rho. So here A is constant, right? and epsilon naught is constant, rho si is constant, only the variable is rho. So if I plot this on the graph, what it looks like is, here this is E and here this is rho. So for a 0 to a range it is 0. If I show by a different color, if I show this here in this range, it is 0. Suppose here is my radius a, and on this range the value gets maximum, and that value will be when rho becomes a. So a gets cancelled, it is rho si by epsilon naught, and after that what happened is there is decrease, there is decrease. So if I make it properly, it is not square of the distance, but it is inversely to the rho. So, and also after this reaches what, b, after this reaches b, so after that also it becomes what, 0 only. After that only it becomes 0. So after that it becomes 0. So here the distance is b, the radius is b. So you can plot this on the variation of E with radius. So this is about the E and D due to coaxial cable. Understand? Now we will see next topic, that is E and D due to uniformly charged sphere. Now this sphere is uniformly charged. So what it means is that charge is not only present on its surface but also inside this sphere. So here this charge having some volume charge density, suppose its volume charge density is rho v. So volume charge density is rho v. So what will be the what will be the value for rho v if I take this charge, this sphere has charge q, so divided by its volume. So what will be the volume of this, 4 by 3 pi, and I'm considering the capital R as its radius of the sphere. So this value will be the charge volume charge density. So I can write q in terms of the volume charge density, it will be rho v into 4 by 3 pi r cube. This relation will be used in the next cases. So now I want to find E and D, this due to this uniformly charged sphere. So again I have to find in the all regions, that is inside, on its surface, outside the sphere. So let us consider the first case where I'm considering a Gaussian surface. Now what is the Gaussian surface I will take? As this is a sphere, so I will take Gaussian surface as sphere only. So I will take a Gaussian surface such that the Gaussian surface is inside the sphere. So for case 1 I will say the radius of the Gaussian surface I'm taking as small r, it will be from 0 to the value less than r. Okay, so let us apply Gauss law here again. So what the Gauss law says, it says is d dot ds will be equals to the charge enclosed. Now for a Gaussian surface which is inside this sphere, what will be the value of charge for this Gaussian surface? Suppose this is my Gaussian surface. What is the value for charge for this Gaussian surface? So as the charge is uniformly distributed, so it will be the volume charge density multiplied with this this volume of this sphere, yani ki जो गॉसियन सरफेस हमने लिया उससे उसका वॉल्यूम हम मल्टीप्लाई करेंगे वॉल्यूम चार्ज डेंसिटी के साथ, दैट इज रो वी इंटू 4/3 पाई small r cube, right? That will give the total charge which will present inside the Gaussian surface. Now this d dot ds, now the d and ds vector will be, as this is a sphere, so ar cap, and d vector is also ar cap, so this becomes d integral ds equals to rho v into 4/3 pi r cube, right? This will be the value. Now what will be the ds? Ds is the surface charge of the Gaussian sphere, so it will be d into 4 pi r square equals to rho v into 4/3 pi r cube. Now if you simplify this, so if you simplify this, what will be the value of d? It will be rho v, here this 4 pi and this 4 pi gets cancelled, here r square makes this power gets cancelled, and the remaining things are rho v multiplied with r divided by 3. This will be the value of d. If I write in vector form, so it will be like this, because r component will be there. So d vector is equals to rho v r by 3. And if I want to write the E for this, it will be simply divide this by epsilon. So I am taking as free space, so I will write epsilon naught. So depending on the medium, you can write epsilon. So this will be the value of electric field intensity inside the this uniformly charged sphere. Inside the uniformly charged sphere, the value of electric field intensity, it will be rho v into r by 3 epsilon. Now here you can see that E is varying directly with the radius, directly with the radius. So E is varying directly with the radius. So here the electric field gets increases with the if I increase the this radius of the Gaussian sphere. Now we'll see case 2. If I consider the Gaussian surface on this sphere only, if I consider the Gaussian surface on this sphere only, that is when the radius of the Gaussian surface is capital R only. So let us say this is case 2 where R and R are same. For this surface, if I apply the Gauss law, total charge enclosed becomes the total charge of the this sphere. So this uniformly charged sphere, so I can write it as rho v into volume of the sphere, that is 4/3 pi r cube. And here if I solve this, so it becomes d, and integral of ds will be the radius, there will be the surface area of the sphere, which is 4 pi r square. Here this rho v into 4/3 pi r cube, and as r is equal to r, I mean the small r is equals to the capital R, so here I can replace this r by a small r by a capital R and cancel these powers, and the final value of d will come as, if I write in vector form, it will be rho v into r, or this r will get cancelled, in fact rho v into r, no, not get cancelled, rho v into r by 3 ar cap, and value of E, it will be rho v into r by 3 epsilon naught ar cap, right? So this will be the value of the electric field intensity at the surface of this uniformly charged sphere. ठीक है, अब दूसरा चीज, मतलब तीसरा केस, for the Gaussian surface, if I consider Gaussian surface outside this sphere, outside this sphere, यानी कि इससे बड़ा स्फीयर हम कंसीडर करेंगे. So let us say this is my Gaussian surface now. This is my Gaussian surface having radius small r. So for this, the charge is completely enclosed. The charge of the uniformly charged sphere is completely enclosed in the Gaussian surface for the radius value, which is from r, capital R, to infinite, let's say. So again, applying Gauss law, total charge enclosed. So what is that? The total charge of the conducting sphere, that is nothing but the volume charge density multiplied by the volume 4 by 3 pi r cube. So this becomes d, and integral of ds makes it 4 pi r square. So if I solve this, so many things gets cancelled. 4 pi from here, and the value of d, if I write in vector form, will be rho v multiplied by r cube divided by 3. This will be the value of d, and the direction will be ar cap. And if you want to write the electric field intensity, simply divide the value of this electric flux density by epsilon naught, or depending on the medium by epsilon. So this will be the value. Something is missing here, I believe. Here r square does not get cancelled. Here this is r square. Here also there is r square. So here also r square, here also r square. Now you see that the electric field intensity when the Gaussian surface is considered outside the this uniformly charged sphere is varying with the radius as inverse to the square of the distance. Inverse to the square of the distance. So now let us plot the variation of E. Variation of E with R. Variation of E with R. So let us plot this magnitude only. So first I will write what is the value of E. So for the Gaussian surface smaller than R, it was rho v R by 3 epsilon not AR cap. Just we have solved here, not here, here. Rho v R by 3 epsilon naught. Now for case 2, when small r becomes capital R, it is rho v into capital R by 3 epsilon naught. Rho v into capital R by 3 epsilon naught. So I can write this value as rho v into R by 3 epsilon naught. Same it will be for R equals to capital R. Small r equals to capital R. Now for the final value, that is R varying from capital R to infinite, but it was rho v into r cube by 3 epsilon naught r square. Rho v into r cube bound by 3 epsilon naught r square. You see here. Now I want to plot this on the graph so that I can see how the E varies with the radius. How the E varies with the radius. So let us plot. So when the radius begins from 0 to r, it is varying directly proportional with the radius of the Gaussian surface. So if I plot this, it will go linearly increasing up to some maximum value, till it reaches to the radius of the conducting sphere. And what is that maximum value? It is rho v r by 3 epsilon naught here. After that, it is decreasing inversely to the square of the radius, so here it is like following inverse relations to the square of the distance, and here it is following direct proportion. So that's why in the inner part of the sphere, uniformly charged sphere, it is increasing with the radius of Gaussian surface, and after that when the sphere when we take the Gaussian surface outside the sphere, it is decreasing as the radius of the Gaussian surface increases. So this is the variation of E due to a uniformly charged sphere. Understand? Now let us see this question based on the previous thing which we have done, that is volume charge density due to charge sphere. Calculate the field E at r by 2 and E at 2r due to volume charge as sphere of radius r and volume charge density rho v. So we have done this thing right now. So we have to calculate the electric field intensity at r by 2 distance and at 2r. So for r by 2, the Gaussian surface is inside the sphere. So for that, what will be the relation for electric field intensity? It was rho v into r by 3 epsilon naught. Right? Just now we have done this. Rho v into r by 3 epsilon naught. So I can use this relation. So what will happen now? Rho v into r. Here I want to find the electric field intensity at r by 2. At r by 2. So E at r by 2 becomes rho v. R by 2 upon 3 epsilon naught, it will be rho v r by 6 epsilon naught. So this is at r by 2. So from the given option, these two gets eliminated. Now I want to find the electric field intensity at 2r. So 2r, for 2r, the this is outside the sphere because the sphere has radius of r. So we have to follow the relation of outside the sphere. What was that? It was rho v into capital R cube divided by 3 epsilon naught small r square. So rho v into capital R cube divided by 3 epsilon naught small r square. So what is small r we have to take as 2r. So it will be rho v into r cube divided by 3 epsilon naught here r square. So what the value of e to r becomes? E to r becomes, we have to take only magnitude only. So this will be gone and here it is 2r actually. 2r square. So if you simplify this, rho v r cube by this 2 square becomes 4, so it becomes 12 epsilon naught r square. This makes this cancelled and rho v r by 12 epsilon naught will be the correct choice. So here this is not correct, this is the thing which we have to choose, right? You see that rho v r by 12 epsilon naught for e to r, and for r by 2 it is rho v r by 6 epsilon naught. So this is the correct option. Now let us see one more problem. Here spherical surfaces at r equals to 2 and r equals to 4 carry uniform surface charge density of 40 nanocoulomb per meter square and 4 nanocoulomb per meter square respectively. The radial flux density and at r equals to 3 is given by dash nanocoulomb per meter square. So we have to find the radial flux density, that is nothing but the electric flux density or the displacement flux density from these option whichever is correct. So let us find out what will be the correct answer for it for this. So here there are two basically spheres. Suppose this is r equals to 2 surface and this is r equals to 4 sphere which I am making. here it is R equals to 4 surface. It is having charge density as 40 nanocoulomb per meter square, and it is having 4 nanocoulomb per meter square, and I have to find the displacement flux density at R equals to 3. So what I have to do is I have to consider a Gaussian surface at R equals to 3. Now what is Gauss law? Gauss law says that d dot ds of q enclosed, charge enclosed. So you can see that for this R equals to 3 Gaussian surface, the charge enclosed is only this, which is R equals to 2 surface charge, and it does not matter the charge of R equals to 4 surface. R इक्वल्स टू 4 सरफेस पे जो चार्ज है वो मैटर ही नहीं करता इस केस में, जिस केस में हमको सिर्फ और सिर्फ R इक्वल टू 3 सरफेस पर जो भी चार्ज इंक्लूड है वो कंसिडर करना है सिर्फ और सिर्फ। तो उसके लिए R इक्वल टू 2 सरफेस वाला चार्ज ही कंसिडर किया जाएगा, एंड द वैल्यू ऑफ Q enclosed will become surface charge density of this R equals to 2 surface into the surface area of this R equal to 2 surface. And here if I solve this d dot ds, what it will become? It becomes d ds, and ds will be the surface area for this Gaussian surface. So it will be 4 pi into 3 square equals to the charge enclosed. It is rho s at R equals to 2 is 40, and I am writing 40 only because I have to give answer in nanocoulomb per meter square. So 40 into the surface area is 4 pi into radius of the this surface R equals to 2, that is 2 square. So it becomes d is equals to 40. So 4 pi and 4 pi gets cancelled. Here 2 square becomes 4, here 3 square becomes 9, and it goes down. So if you solve this, it comes as 160 by 9 nanocoulomb per meter square. So from the given option, this option is correct. So this is how you can use Gauss law to solve this problem. Now that will be all for today. We will meet in the next video and we will see electric potential. So thank you.